Greetings. I would like to thank you for tuning in and the organizers of Trends in Magnetism for giving me the opportunity to present the investigation of caustic spin wave beams in soft thin films that my colleagues and I have started at the Technical University of Munich. In this presentation, I would like to begin by giving you elements of context about caustic phenomena in general, as well as a few reports of caustic spin wave beams in the literature. Then I will move on to describe the theoretical model that we've used and some of the results that we have obtained with it. Finally, I will present a conclusion and some prospects to this work. Let us begin with some context. I'd like to discuss the word itself, caustic, coming from the Greek kaustikos, aeon, with the meaning of burning or corrosive. In the context of wave propagation, the burn refers to strongly localized and contrasted amplitude features. And mathematically, if you consider the envelope of a wavefront, caustics are the sets of points such that two rays or more are contributing to the wave amplitude. Let me illustrate this with the first example from the field of radio waves. Here you see the emission of a point source into the ionosphere. And quite clearly, there are regions of space where the density of rays is stronger than in others. And this is due to the fact that the inhomogeneities in the propagation medium lead the wavefront to distort and eventually to fold onto itself, leading to the appearance of caustics, here highlighted in orange. Inhomogeneities in the propagation medium are the first reason why caustics may appear, the other one being anisotropies in the dispersion relation. If they are strong enough, then around specific wave vectors, which will be from now on referred to as caustic points, the direction of propagation, which is that of the group velocity, can be stationary, leading to many wave vectors contributing to the wave emission into those directions. This is the phenomenon that is well known, notably in the context of phonon propagation. That's why the image I'm showing here comes from a study of ballistic phonon imaging in germanium. In that study, the authors were able to identify directions of very strong emission, which are phonon caustics. Since we know that the dispersion relation of spin waves in thin films can be strongly anisotropic, we may wonder whether caustic phenomena can occur there as well. And the answer is yes. We are by far not the first ones to tackle this topic. Indeed, caustic spin waves have been observed, for instance, using Brillouin light scattering, as in this study by Demidov and co-workers, where caustic spin waves could be stimulated by the scattering of a spin wave propagating in a waveguide into a full thin film of permalloy. But caustic spin waves have also been studied with theory and simulations, as in this study by Kim and co-workers. What is represented here on the top are the so-called slowness curves, that is to say the set of accessible wave vectors at a certain frequency. Superimposed in blue are the directions of the group velocity, which, as you can see, are stationary around certain specific wave vectors. So we are dealing with caustics. They correspond, mathematically speaking, to a divergence in the spin wave directional power density. And this is confirmed in the simulations, which reveal very clearly defined directions of strong spin wave emission. But what I also want you to keep in mind is that even though in those two cases we are dealing with two caustics, those actually merge into a single caustic spin wave beam at a certain threshold frequency, above which there isn't any caustic point anymore. This phenomenon will be referred to again later on in the presentation. But now that we know a bit more about caustic spin wave beams, I'm going to present the theoretical model that we've used to describe them. It takes its roots in the dispersion relation that has been derived for spin waves in soft thin films by Kalenikos and Slavin. You can see that it's quite a bulky equation. There are lots of terms depending on the film thickness, on the applied field, on magnetization, and on the exchange constant through the dipolar exchange length. And finally, you can see that the dispersion relation is anisotropic due to the dependence on the wavefront angle, which is defined from the applied field or magnetization to the wave vector. Now, in order to be as general as possible, and in order to make things simpler, we start by normalizing the excitation frequency to magnetization, the wave number to the film thickness, the dipolar exchange lengths to the film thickness as well, and the applied field to magnetization, which allows us to rewrite the dispersion relation in this completely dimensionless form, leading to the appearance of this function omega, with the wave number and wavefront angle as variables, and we are left with only 3 independent dimensionless parameters. Now, a few things must be noted. This function omega defines the slowness curves if it is set to a constant, of course. It possesses 2 mirror symmetries, which means that we can focus only on one quadrant and generate the whole curve using those mirror symmetries. And finally, since the group velocity is nothing but the gradient in k-space of this function omega, then we know that the group velocity will be perpendicular to the slowness curves. Let me illustrate that with a couple of examples that have been calculated for these experimental parameters. You see that the shapes of those slowness curves strongly depend on the frequency. And if we define theta v as the direction of the group velocity, we see that there are specific points highlighted with markers where the direction of the group velocity is stationary, meaning that we have one caustic point on those curves. And since around the caustic point, the direction of the group velocity behaves quadratically with the wave number, it means that the caustic points geometrically correspond to inflection points of the slowness curves. With this in mind, we may now wonder what we can investigate about the caustic points. The main properties of the caustic points are obviously their position on the slowness curve, denoted by the caustic wave number and wavefront angle. And of course, we can be interested in the direction of the corresponding caustic spin wave beam. And this is what we record in our study. Since we want to be as close as possible to experiments in which one investigates a single thin film at a time, we start by fixing the ratio of dipolar exchange length to film thickness. Then we can sweep the applied field and the excitation frequency. So nu and h are arbitrary. To be more precise, we start by fixing the portion of the field and frequency plane that we're going to investigate. We furthermore restrict ourselves to fields below the ferromagnetic resonance field. And for each point, we reconstruct the slowness curve. We scan it to find the caustic points or caustic points. At this stage, I must note that there can be 1, 3, or even 0 caustic points on a slowness curve, but I will not have the time to discuss further the case where there are 3 of them. And finally, of course, we record the reduced wave number, the caustic wavefront angle, and the corresponding spin wave beam direction. Let me start the discussion of our results by showing you what such a scan in field and frequency can look like. Here, I'm showing an example for a specific value of the number eta, and you can immediately see that both the reduced wave number and wavefront angle show not too dissimilar and non-trivial behavior, where we can identify several interesting features. We have a low frequency pocket that seems to have a rather sharp boundary, and eventually we have an upper boundary to the whole region where caustic points may arise. And in the following, I'm going to discuss these 3 features, working my way from the bottom to the top. Let us then start with the low frequency pocket. It corresponds to caustic points that are deep in the dipolar dominated regime. Namely, we can predict that the caustic wave number behaves proportionally to the square of the excitation frequency. Moreover, we can predict to the lowest non-zero order the position in terms of wavefront angle and the direction of the caustic spin wave beam. And these predictions nicely match what we find numerically. And I want to stress that this behavior is not contradictory with this finite value of the wavefront angle that is not pi/2. Indeed, this corresponds to a case where the slowness curve extends far above the caustic wave number and varies very rapidly in terms of orientation below the caustic wave number. Now, I'm moving on to the boundary to this low frequency pocket, and more specifically, I will focus on the point at 0 applied field. This corresponds to a very sharp upturn in the wavefront angle and in the caustic wave number due to the fact that the slowness curve becomes very flat around the caustic wave number, and it becomes straightest at a certain pair of reduced dipolar exchange lengths and frequency, which can be found out using the combination of analytics and numerics. And this case corresponds to a caustic point of higher order in the sense that the direction of the group velocity behaves not quadratically, but in a quartic way around the caustic point. But still, even though the wave number varies a lot if we go across the caustic point, it must be noted that the spread in wavelength is still low due to the fact that the effective wavelength seen in the caustic spin wave beam depends on the projection of the wave number onto the group velocity direction. And this, in fact, varies very little across the caustic point. Finally, I have also investigated this upper boundary, which corresponds to, in fact, the case where the slowness curve is very straight and the caustic point goes to a wavefront angle of pi/2, and the direction of the caustic spin wave beam is also pi/2. If you remember the mirror symmetries of the slowness curve, then you see that this specific case corresponds to two merging caustic spin wave beams that form a single caustic spin wave beam at this frequency, which means that you get twice the amplitude and only one direction of strong emission, which is very interesting for applications. And furthermore, since the slowness curve is tangent to a circle of constant wave number, we can expect the spread in wavelength to be even lower than before in that situation. In order to get more precise ideas about how those conditions can be reached, I have investigated the frequency of merging at zero applied field as a function of the reduced dipolar exchange length, and this produces this behavior. We can also look at the corresponding wavelength of the caustic spin wave beam as a function of eta, and you can see that unfortunately, for reasonable values of this parameter, the wavelength is actually rather low, which means that the observation of this merging phenomenon will probably be quite difficult, except in ferrimagnets such as yttrium iron garnet with a large dipolar exchange length, and the method of choice would probably be time-resolved X-ray microscopy. With this, I'm now going to conclude this presentation. I have shown you that either the folding of wavefronts or anisotropic dispersion relations can lead to caustics. In the context of soft thin films, caustics arise at stationary directions of the group velocity, so at inflection points of the slowness curves. And these have been shown to exhibit a quite rich behavior. We have discussed the presence of a low frequency pocket with thickness independent properties. Then I have shown you that the boundary to this pocket can feature a caustic point of higher order. And finally, I have shown you that the boundary of the region where caustic points exist corresponds to a strong and single caustic spin wave beam that should feature an even lower spread in wavelength. Finally, in terms of prospects, we are looking at how to quantify the enhancement of amplitude due to the presence of caustics. And we have started experiments using mostly time-resolved MOC in order to look at caustic spin waves using such kind of microstrip antenna. And we are beginning to see caustics that are nicely matching our theoretical predictions. And with this, I would like to thank you for your attention.